didn't have final. We just got the whole. How is this?
Yeah, they're like we have few papers and no final.
It's good.
Yeah, and there's still checking papers. Still have to hand out the third one. My partner is in charge of it because I didn't first two. He's doing the second, third one. So but previous semester I had a problem with testing machinery and the whole machinery in this industry. So it's a very big course. Do you remember the machinery?
Indeed.
Wow, big course. Material.
Yeah.
It's a very good course. A long time to study. We have the test. The test was not that easy. It was a computational things. Sure. I'm gonna start taking this semester. Start to take the lectures. I think I'm gonna take. I'm definitely gonna take MLOps. I think it's important. I mean, if you're in the field of AI, you have to know deployment, and you have to understand basics of deployment. Not that it's that hard, but you just have to be aware of things. What else? I think I'm gonna do audio and deep learning as a
Like this. No.
Yeah. What are you gonna take?
I took NLP first.
You took NLP? How was it?
It was great.
It was great?
Yeah, it was great and fun.
Yeah.
But we started from scratch, like from very basic language model, and then we moved to I'm doing the final project. The final project is about the word model. It's about the settings word models in Hebrew.
Oh, perfect.
Yeah, word. We word transform stuff, and we also had a midterm.
Yeah, I have what? No, it is good. Yeah, he's a good friend of mine. He is with you. This semester you did? Yeah. But he's also doing the third. The project now that you have to handle.
It was a great course if you were interested in it.
Yeah.
Wow. Shut it off. Go ahead.
Maybe so. How are you?
I'm good. How are you?
Good. You gonna teach us the workshop?
So I'm the teacher.
Oh, cool.
My name is Kyle.
I'm David.
Hi, David.
I'm doing the MSc here in MLDS, the machine learning.
That's very nice. I actually graduated my bachelor in
In
science in Reichman,
Wow.
and then I did my master in Arizona State.
Oh, what did you do there? How did you land there?
How did I learn there? It's actually pretty nice. The course is very nice.
Yeah.
But then I think like Reichman is the best.
Yeah, right. So how long? This is still 9, right? Today till 9.
Yes, it's 2-9. So I'm going to do our hands-on. So if we like to finish that earlier, we can do it. So how do you find the course so far?
Actually, I did this semester deep learning. So I'm not sure if you give this workshop only to people who do deep learning. I'm not sure. I'm not aware of it. Deep learning was a good course. The problem was that at some point in time, it was very complex to understand without seeing the code. Transformers and stuff like that. You have to really touch it to be able to understand it better. But it was a very good course. It's very important for subject. I mean, for people who are doing data science. I think it's one of the most important subjects in deep learning. Everything here, everything is deep learning today.
Yes, right.
And also the stuff. In classic machine learning is pretty, I mean, less and less people are using it. And the complex problems are in deep learning. So you have to really have a good notion of how it works and also have a foundation in terms of code. And it really all depends on what you're going to do with it. I mean, if you want to be what is Sahir, if you want to work for other companies, that's one thing. If you want to do your own thing, then you have to really understand really well the subject, know what you can do with it.
So you're also working in the data science field?
Actually, I'm only studying now. Took about a year off now.
That's so cool.
Yeah. It's also not that easy, just to study, but it's cool. And you're working?
Yes, I'm
Where?
I'm working in Macau. Actually working in Sora's group, in Sora's lab, doing research, and I'm also working in lab like doing AI in healthcare, in medicine, building predictive models for different kind of diseases, for heart disease, diabetes.
So in the healthcare industry, so it's very good. Very good. And who's in the workshops? You and
Me and today, like I'm the teaching assistant, so I will do this
and you see
lecture.
that, right?
Yeah, and also Ellie is the lecturer.
Yeah.
I will be assisting her throughout the workshop. So she is the lecturer, and I will help at the hands-on coding section.
Cool.
But like today, I'm doing this lecture today.
Cool.
And also the hands-on coding section.
So what are we going to talk about today? The basic of GAN, like
GAN, and also there are different type of GANs and about unconditional generation and also conditional generation. Because the classic GAN you cannot really control the output. So at the end we will also learn about how we can control the output of the generator. So, and then Elle will talk about another kind of generating photos. Like she will talk more about the generation model.
Cool. Very good. Very good. Very good. So you live in Israel?
Before I lived in Israel. When I studied here, I lived in Israel. Now I don't live in Israel.
You don't live in Israel?
No, I don't.
So where you're in the US?
I was in the US, and I was also actually like based a lot in Macau. So actually after the COVID, I come back from Israel, and then I'm in Macau. So sometimes I'm in Hong Kong.
Could be there.
I hope you enjoyed the workshop.
اللي بعمله مثلا فيزيك عشان
هو
number 5.
fine class. Fine.
تجد بعض تصير تجد
شغال مدرج. Yang dibagi.
Okay. We're going to take him later.
Wah, terus yang dibagi.
Check that.
Hello.
Yeah.
Hello.
Yeah.
Hello.
It's like that again, so. Like
No.
again.
Is it on? Yes.
Like again.
Was it okay? It's that's fine.
Hello. I'm.
Yes. It's
Yeah.
game. So it's fast. Maybe
Hello,
Yeah.
hello.
let's do that. No. Not about the end. Medication. Running out. Yes. I'm doing content. You want it. This is. So. This is. Then. In high.
Two more lectures.
Wait 4 more minutes, or maybe even more. Just to make sure everybody is okay with deep learning.
Yes.
Right.
حاسس ان التوهان ما الترانسبورت كان الشعب gaming so gaming that's that
Go on, they go on down.
yeah
They go down there.
it's like the
They did. Yeah.
This,
Okay, let's start because my part is, if anybody's late, it's not that terrible, because my part is not that important. So first, I want to thank Abigail for coming here to discuss with us, coming here to do this talk with us. And tomorrow you will meet Yael, Dr. Yael Winkel, who's going to do the lecture for the rest of the workshop. And I'm very happy to see all of you here and to start this first instance of this workshop. So I don't know if you've been to program workshops before, some of you may have. We're doing these every once in a while. It's meant to be a combination of theory. It's not very deep theory, but theory in terms of explaining the methods, as well as actually doing things hands-on, which is what you're going to do both today and in the rest of the workshop. So going into the details of the methodology, and then actually doing it. So of course you cannot do everything hands-on. So the guy and Yael selected aspects, specific aspects that you are going to do hands-on, and all the rest are just going to be introduced on the more theoretical level, but you can explore them, and I think they're going to give you pointers on how to explore. Yes, what else? So we're going to try to record that, but I think it's important to come to class and do the hands-on in class. That's the idea. If you can come, that's much better. Okay. And yes, as I said, so today, Abigail will talk about GAN, which is, so I should say that the idea of GANs, which is maybe the first form of generative AI, not the first, maybe VAE was before. There were other approaches before, but I think this idea of GAN, which Abigail will explain, is certainly one of the most interesting developments, I would say, in machine learning, not only in deep learning. In general, in machine learning, this idea of what makes GAN work, what makes GANs work, is one of the most interesting ideas of the development of machine learning. As you will see, and as you will practice at the second part. So today we're going to do GANs. Tomorrow, Yael will give an introduction to, in general, what are generative models. And then in the next 3 days, it's going to be mostly diffusion, correct? Right. And Abigail will be with you for the rest of the workshop for the technical parts, as well as the hands-on part at the end of the lecture. So Yael is going to lead the lecture, and then Yael and Abigail are going to do the hands-on at the end. I think that's it. So I think with if there are no further general questions, again, I'm happy that you're here. Then we'll let Abigail start with GAN. I'll stay for a little bit.
Thank you, sir, for the introduction. So, my name is Abigail.
Yeah, you should introduce yourself more. What you're doing.
Sure. So, my name is Abigail Bach. I'm a graduate in Bachelor of Science in Reichman University. And then I also did graduate from my master in computer science recently from Arizona State University. When I studied in Reichman, Professor Sommer was my professor in data structure and then in machine learning. So, and then I also work, I have been working in source group to use AI to in medicine. And also, I'm also right now working in a university in Hong Kong doing data science work in the lab. It's also the data is also on medical data. So I'm building a predictive model to predict different kind of disease, cardiovascular disease, diabetes, cancers, etc. So today we will be talking about generative adversarial network, GAN. So first we will go over a little bit intro to GANs. We will be talking the basic concept of a vanilla GAN. This is the simplest form of GANs, and then we will go over the convolutional GANs. There are different kinds. So we will talk about the convolutional GANs or DC GAN, and then so both of these GANs, vanilla GANs and the DC GANs that we are going to talk about, is a kind of unconditional generation. Meaning that you cannot control what image, output of the generator you will generate. You cannot control the class of the images. So we are going to also, lastly, we will be talking about conditional generation and controllable generation. And then at the end of the theoretical part, we will do a hands-on section, hands-on coding section. So I've sent you guys the tutorial, so we will be needing that at the last part of the lecture. So what are generative models? Generative models are models that are given a noise, and then it will output a features. So noise can be a scalar, like 2, 3, or -4, or even most of the time is a factor of these numbers. And then you will output features X, like for example, some pixels of an image. And here we see also that the input there is a class Y here. So this is optional. So for right now, for now, we are learning vanilla GAN. So we won't be needing this class Y as input. But later on, when we learn about conditional generation, we will need the class Y here. So for generative model, the model is actually learning the conditional probability of feature X given the class Y. So in contrast to discriminative model, what we are going to input is some feature X. For example, in this case, maybe small ears, small eyes, it meows or it barks, or even some pixels, such as an image. And then it's going to output a class Y. So it will output if this image is a cat or a dog, or even some endless digit, like 1, 2, 3, like later on we'll see in the lecture. So in a discriminative model, it's about to learn the probability, the conditional probability of class Y given X, given feature X. So there are different types of generative models. So there are variational autoencoder. Maybe you hear about it. So the variational autoencoder makes up of two parts. The first part is an encoder where you input an image into the encoder and it output a distribution of the latent space. And with this distribution of latent space, you input into the decoder, and the decoder is going to output an image, a highly realistic image. And then afterwards, you will save the decoder, and then you input some distribution of the latent space, and you can generate some realistic images anytime you want. So in contrast to generative adversarial networks, which we will look into today, so the GAN consists of a generator and a discriminator. and they are actually competing with each other. So later on in the coding section, we will see how this competition in action. And after this competing with each other, you will both the generator and the discriminator is trained to perform at a certain good levels, good performance. We will save the generator parameter, and then when you input any random noise, it will generate a highly realistic images. So,
What was the motivation to come up with the generative adversarial networks if we've already had the variational autoencoders for the generative model? Like, what is the difference? What was the incentive in the first place?
So first of all, we don't always like the input is different. So sometimes and it's more easy to come up with a random noise and different like the variational autoencoder and the generators and the GAN have really different usage. So in some usage the autoencoder is performing better, and in another case the GAN is performing better. So you need to have these models to see what gives better in performance in your use case.
I guess is what I'm asking is chronologically, which type of model appeared earlier? The variational autoencoders, right?
Yes.
Okay.
Right. And
so later on, when people came up with the idea of GANs, they had some motivation, some incentive to come up with this type of generative model. So I'm just asking, like, what was the main drive for that?
So what is so special about GAN is that these two models is training each other. So the discriminator is actually feeding back to the generator, which we will see later on. So this is really some the cutting edge part of being GAN and being different from this variational autoencoder.
I understand in terms of mechanism there is a significant. I'm just asking, like, why would you come up with this type of model in the first place? What are the disadvantages, I guess, of variational autoencoders?
You always want to improve performance. You can ask the same question about the future, which you're going to start the day after tomorrow. I mean, after GANs, what's the need for the future? If you ask me, maybe there is. You ask Gael, certainly. The performance is much better in certain things. There are still certain things that GANs will do better.
Got it.
Simpler.
Yeah.
So, being faithful to the training, for example, is one of the things for the pictures to really look realistic, or whatever object you generate to really look realistic. I think GANs perform better than VAEs. The VAEs don't have that as one of the GANs were as a guy will explain the design, fool the eye of the beholder to think that the object is.
So thank you for the question. It's really nice discussion. So here is GANs over time. So here we see a Wilton Goodfellow, who is proclaimed as the father of GAN. So GAN have only been around for 2014, and it has already achieved super desirable performance across a multitude of tests. So here we can see the image in 2014, which is generated by GAN, which is still in black and white. And in 2015 and 2016, it starts getting like colored image. But if you look closer, you can see all the pixels, and there are some artifacts and the hair, etc. And in 2017, 2018, like you can see that the images start getting really realistic, and until 2020, these images are produced by style GAN 2, which like we can see the face are super realistic, and we got like even some soft background at the back. And here we are going to talk about some application of GANs. So this is a GANs for image translation, and we can see here is some output of the cycle GAN where it is used to turn a horse video into a zebra video, and it can be done vice versa from a zebra back to a horse. And here is another example where we input a Mona Lisa picture. And actually an actress of who doesn't look like Mona Lisa at all doing some kind of videos, and then combining these two inputs, we can generate a video of Mona Lisa with different facial expression and poses. So GAN not only produce 2D images but also 3D objects. And here are some companies using GANs. Adobe is using GAN for next generation Photoshop. Google is using GANs for text generation. IBM for data augmentation. Potato Snapshot for image filter, and Disney for video resolution. So we're going to talk about some generative adversarial network GAN intuition here. So in the GAN literature, the generator is always being seen as the art forger. Is trying to learn to make fake images that look real. In contrast to the discriminator, is always being referred to as an art critic. It learns to distinguish between real and fake. So here is a high-level architecture of the GAN. So here we see the GAN is made up of the generator and the discriminator. We will input a random noise into the generator for it to generate some fake images. In this case, is an endless data set. And the discriminator will take on this fake image together with the training set, some real endless data images, for example. And then you will both fake image and the training set will go into the discriminator. And the discriminator will output the probability that these images is real or fake. So here we can see the loss function over time. Just now we mentioned that the generator and discriminator is actually in a competition. So we'll see how their loss function over time in here. So in the beginning, both the generator and the discriminator are bleed it out. So you can see that the most of the generator is pretty high, like in the beginning. So why? It's because the generator's image doesn't look real at all. But then over time, like in around 25th to 75th apples, the loss drops, and it's because the over time the generator learns how to produce more realistic images. And then from around Apple 75 to 200, the loss increased slightly. Is mostly due to because it's overtrained. So ideally, we will stop the training at around Apple 75 here. So as for the discriminator, so one thing to actually I need to mention is that the discriminator's test is to distinguish between the real and fake. So the output is only one number, which is the probability that the input is real. But for the generator, you got a more difficult task. Like its output is an image. For example, if it's an endless digit, you'll get 28 by 28 pixels. They have like 28 times 28 outputs. So in this case, the generator has a more difficult learning task here, and it's more difficult to train than the discriminator. So here we can see that the discriminator is the loss starts by low, but then it increases over time. Is because the generator learns how to get to output more realistic images, which makes it hard for the discriminator to distinguish between real and fake. But then over time, the discriminator is also getting better. So the loss of the discriminator declines. So we see that there is a competition. Yes.
Aren't the loss function of the generator and discriminators are complementary?
Right.
Sorry?
Aren't the loss functions, the generator and the discriminators, complementary? Don't they complement each other? Like let's say for a given sample, if the generator manages to pull the discriminator, right? Then for this sample, the generator gets a positive score and the discriminator gets a negative score, and vice versa, right? For each sample, a success for the generator is a failure for the discriminator, and vice versa. Yes. So I would expect the loss functions to be complementary, right? The curves.
What do you mean by complementary? So here we see that when at epoch 25, the generator gets like the loss is pretty low. It's because it gets.
But it is complementary. At 25, this the epoch of the generator
Not
is
precisely though.
pretty complementary.
It's not the same
It's
batch.
not exactly the same because it's not the same function.
So you don't use the same batches.
Yeah,
Oh.
They
it's not
don't
the same.
complement one.
Yeah,
Are
they're complementary.
They go against each other.
They go against
Exactly.
each other. It's shown here. They go against each other.
It depends
But
on
not in the same ranks.
You will see also the specific implementation depends on which loss you use, because they go against each other.
Right. Yeah.
Can I have a question?
Yes.
What is the sweet spot when I'm looking on the loss curves? Like what is my goal to achieve? I want both of them to narrow down to a linear curve. Like what is the sweet spot that I'm looking for in these curves?
Okay, so what we care about is basically the generator. The discriminator job is just to give feedbacks to the generator to improve the generator. What we care about after training is actually the performance of the generator, and it will output realistic images. We will at the end of training we save the generator's parameter, the model. So I would say that at epoch 75 we can like stop training the generator and we will save the model, so we will be used later on to generate realistic images.
And now can you make sure that it's not because the discriminator is not good enough?
Lousy. So we will see in the next. So this is also an indicator that we can stop training. So this is the predicted probabilities of the discriminator. So in the x-axis is the epoch, and in the y-axis is the predicted probability that the images are real, predicted by the discriminator. So in the beginning, the discriminator is lousy. Oh, okay, and you can see that the blue line is the predicted probability that the images are real when the input images to the discriminator is real. And the orange line here is its counterpart, but then when we are inputting fake images to the discriminator. So we can see in the beginning the discriminator is really lousy. So even for fake images, it gives a really high score, like 0.65 for fake images. So, but then over time, the discriminator also gets better, and it at epoch 25 it gives a really low score to starting to give low score for fake images, and we can also see that the generator is able to generate more realistic images, and it's really hard for the discriminator to guess if this image is real or fake. That's why we can see that the full score converges to 0.5, meaning the discriminator is indecisive. So this is also an indicator that the discriminator is the training is should and these scores are converged. So and this is actually taken from the German notebook that you will be doing in the hands-on section. So you can see this competition in action. So okay. Yes.
The orange curve.
Yes.
Type 4. It's the probability of real given fake.
Real given is the like so here the orange line is here. See, I input the fake images to the discriminator, and then it output the probability that this image is real. So let's go over some question. What is the role of the generator? To find the real image in a pile of fakes, to create realistic looking fake images, to sort images by color, or to piece together real images to make a fake.
Realistic looking.
Correct. Is to create realistic looking fake images. What is the role of the discriminator? To create fake images, to classify images as real or fake, to tell the generator is doing a stellar job, or to rank images based on complexity. Yes, correct. Here, guys.
Check this one, right? It's a tool in the hand of the generator.
Yeah.
Actually, to classify images as real or fake. So let's look into the nitty-gritty detail of the discriminator. So the discriminator is basically a neural network where we input some features representation of image, some pixels, into the discriminator, and you will output the predicted probability of being real or fake. So if I input a real image or realistic image, the probability hopefully will give us a high probability. Whereas if we input some like fake images or non-realistic ones, you will give a low score to the real probability. So let's see the discriminator training in action. So here we have a discriminator, and we are inputting a 28 by 28 pixels representing a digit, the class 8 here, the M-list digit, into the discriminator. And then we give an output. We denote it as y hat, which is the probability that this image is real. And then we input this into the cost function. Along with this y hat, we also put one truth of this image, whether it's real or fake, into the cost function. And the cost function will calculate the cost. And then with this cost, we will use to backpropagate and update the weight of the discriminator. So essentially, the discriminator is trying to learn the probability of y, of class y, given the feature x. In summary, the discriminator is a classifier. It learns the probability of class y, real or fake, given features x, and the probabilities are the feedback for the generator, which we will see in the upcoming slides. So the generator is basically another neural network. So we will input some noise factor into the generator, and you will output some like highly some images. It can be realistic or non-realistic. And note that different noise factors can output different digits or images. So later on, we will learn how to, so different noise factor can output different images. And later on, we will learn how to tweak this noise factor so it will output the images that you desire. So this here is the generator training in action. We can see that the generator here we input a noise in the generator. It can be a factor, like what we've seen in previous slides, and it outputs some features, x hat. So it will be a 28 by, if we are training with the MNIST district, it will be a 28 by 28 pixels of image. And then we input this picture XF into the discriminator. And it will output a probability that if how real this image looks like. Remember, this is a fake image. So if the generator is lousy and the image looks fake, the discriminator will, and hopefully the discriminator is performing well. So the probability here should be low. And with this output inputting into the cost function together with a factors of 1.
What is the factors of 1, and do you output the label of true or false for the, is it the one-hot coding?
No, it's not one. Sorry, it's not a one-hot encoding. But later on we will learn about why we need to one-hot encode. But this is not the one-hot encoding.
Oh, so what do you output for the cost function? The y hat.
So what is y hat? So y hat is the predicted probability. So
Yeah, that understood the word.
yeah. So
What does the cost function look like?
It's like BCE loss. So later on we will go over BCE the binary cost entropy. So, and you can use different kind of cost function. Like you need to find the right cost function that gives the best performance. So, but we will use a BCE loss in this case, and we will talk about it later on. So here the labels is the factors of 1, and this is really the key here, and we will explain why. So after we have the cost, we will use this cost to backpropagate and update the parameters of the generator. And we do this iteratively. So we will explain why we are putting factors of 1 here. We are putting that is because we want the generator wants the discriminator to think that its fake images are real. So you can see here, when in the beginning, when the this is the loss function, criterion is the loss function. So we are looking at the cost function output y hat versus labels y hat. This part, and this is actual code actually. So here we see the first input of the loss function is a factor of 5 by 1 factor, and it's actually the predicted probability that the images are real. And here is 5 images because we have 5 entries here. Each number representing its respective probability that the sample is real. And here at the second entry, we have a factor 5 by 1 factor of 1, which is the target. So in the beginning, when the generator is lousy and it output fake images that does not look realistic at all, so the discriminator can identify it and give a low real score. So here we have a really big distance between 0.1 and 1. And so on, 0.2 and 1 and so on. And until when iterative,
The generator and the discriminator, every one of them has its own loss function. So it's something like in common.
it's 2 different loss functions. The generator have its own loss function, and the discriminator have its own loss.
Okay, so can you take the last slide? But here they have like a cost function.
Oh, yes, but then it's the same cost function. Both are using BCE loss, binary cost entropy, but then basically they update their they have their own things to backpropagate respectively, and they update different parameters.
Oh, okay, so
You can think of it as 2 cost functions.
I mean like the generator has its own loss function. So when I backpropagate on the generator.
Yes.
So I have 2 loss functions, not 3.
Yeah, you have 2 loss functions.
So where we write in the right cost function, it's mean for the discriminator.
Here. Yes, so this is the cost function for the discriminator, and this cost function updates the parameter of the discriminator, and the generator cost function is updating the cost of the parameter of the generator. Is to later on you will see the code, and then you have a clear idea. Yeah. So but yeah, quick question is two loss function, but they are both using DCE loss. So this is when the generator is lousy. It outputs really unrealistic images. That's why you can see that the probability for being real image is really low, and the distance between the target, which is 1 here, is really large, and it's for all the 5 images. And over time, the generator learns better, trains better, and is able to produce highly realistic images. And when it input to the discriminator is saying that is real, and the probability that this image is real is pretty high. So we can see that 0.9 and 1 is for the first image, for example, has a small distance. So this is when the generator knows that the update can end soon, because it's getting better. So after we finish training the generator, we will save the generator parameter, and then we can use it later on. So, and this process of using later on is called sampling. So we will input any noise factor into the saved generator, and then you will output some realistic endless images in this case. So with the first noise factor, for example, you will output 1. With the second noise factor is a different factor, you will output 6. And with another different noise factor, we will output 8. So different noise factors output different digits. But you don't really have any control of what you will get. You don't, if you want to get an 8, you might have to input a lot of noise factors until you are able to generate an 8. And we want to give some more control of the generator's output. So we will learn a little bit later.
Could you please go over the sampling part? What exactly are we sampling here?
So we are trying to generate realistic images. Yes. So in this case, we are generating the endless image, since the endless image is the training set. So if you are using cat images to train your GAN, you will be generating cat images.
Right, but I'm asking, what exactly are we sampling here? What are the samples?
Sampling means simply means that you give some noise, like some factors, and then you put it into the saved model, the generator, and then you will output 1. And these are generated images. It's not something that you get from training sets.
I'm not sure I'm following. What is the underlying distribution from which we sample?
The underlying distribution, we are trying to learn the probability that this generator is learning the probability that given class Y, you will generate X, right? Given class, the probability of feature X given class Y. So in this case, we are learning the probability of generating these pixels. And this 168 here is not something from your training set. It's not something from the endless image. It's something that is generated by the generator. Given this noise factor, the noise is okay, right? It's The noise is some random number, like you can just take 1, 2, and 3, and then you put this into the saved model, and then you generate some endless image, can be an 8. And this image is not something that is coming out from the training set. It's some new novel image, new novel samples. So we are trying to like do this. Of course.
I'm sorry, but I'm still not sure. Totally.
Okay.
What exactly? Where exactly is the sampling process takes place in what you just shown? What exactly are we sampling here? What is the?
Okay. Let's not think about sampling. It's like generating new images. It means sampling here means generating new images.
Is it right to say that when you say sampling, like to sample from the distribution we learn and to give a new image?
Yeah, you can think of it this way. But
the learned distribution with the noise addition. So we're sampling from this like augmented learned distribution.
Yes.
Okay.
Such that you give a noise and you generate some new image. So in general, the generator is trying to learn the probability of the conditional probability of feature x given us y. In summary, the generator produces fixed data. It learns the probability of features x, and the generator takes as input noises, random features. So here we will talk about the binary cross entropy loss function. So here the first part, -1/m and the summation. So m here is the batch size, and this pink square means the average loss of the whole batch. The h here means the prediction. X_i is the features of that particular sample, I, and Y_i is the labels of that sample. It's the ground truth of sample I, and data is the parameter of the model. So it can be the discriminator or the generator, depending which model you're training. So here we can look into what is the output of the function given its parameter. So here let's look at the green table first. So the binary cross entropy function is making up of 2 parts. So we will go over the green part, the first part. So when the ground truth is fake, yi is 0, and hxi data, this part is the probability that the sample is true. So it can be anything, and this part yi for hxi data will be 0 since we are multiplying 0. So it really doesn't matter what the probability is. It's okay, right? This part. And when the ground truth is real, y/i is 1. The hxi data will be 0.99, any number that is close to 1. And the yi for hxi data, this part here will be a number close to 0. And when the ground truth is real, yi is 1. hxi data is a number close to 0. So yi log hxi data will output negative infinity. In other words, if the ground truth and the predicted probability is similar, this term here will output a number close to 0. And when it is very different, when the ground truth and the prediction is different, the output here will be negative infinity. And let's look at the second term here. when ground truth is real, yi is 1. So HXI data, the predicted probability can be anything. We don't care. Since we are doing 1 minus yi here, 1 minus 1 is 0. We are multiplying 0. So we will get 0 anyway. And when the ground truth is fake, yi is 0. HXI data is 0.01. Or any number that is close to 0. So the term here will output a number that is close to 0. And when the ground truth is fake, yi is 0. HXI data is any number close to 1. The term here will output a number that is close to negative infinity. So in other words, when the ground truth and the predicted probability is similar, the output will be a number close to 0. And when it is when they are very different, the output is negative infinity. So and we see the negative sign here in the beginning. This sign is actually turning the negative infinity into positive infinity. Since this is a cost function, we want a positive loss because a negative loss doesn't mean anything. So when the cost or the loss is positive and is a number that is close to infinity, that means that you have a very high error rate. And we need to tune the model that we're training. So here we can see that in graphs, in plots. So the green part is only relevant when the label is 1. So only when our ground truth is 1, this term of the cost function or the loss function counts. So when our ground truth is 1 and the x-axis is the predicted probability that the input is real, and the y-axis is the cost function, is the output of the cost. So we can see that when our predicted probability is close to 0, the cost is actually approaching infinity. Whereas when our predicted probability is close to 1, the cost is close to 0. And in the case of when the ground truth is 0, when the predicted probability is close to 0, the cost is low, is close to 0. And when the predicted probability is the real score is high, is close to 1, the cost function approaches to infinity. So in summary, the PCE cost function has 2 parts, one relevant for each class, for us being the real class and the fake class. So close to 0 when, and the cost function, the loss is close to 0 when the label and the prediction are similar, and it approaches infinity when the label and the prediction are different. So this is so let's put everything together. Just now we have seen the discriminator and the generator, and each of the respective model training in action. So it's time to put everything together. So here again we see the generator and the discriminator. Is an overall architecture of GAN. The generator is trying to make the fake images that look like real, and the discriminator is trying to distinguish the fakes and the real. So we'll input the noise into the generator for it to generate fake images, and we'll input both the real and the fake images into the discriminator, and it will output the score that the input is real. So here is the training of GAN. Wait 1 sec. Okay, so here is the training of the generator. So when we have the generator, we input into a noise. We input noise into the generator, and we output fake images, which we will input into the discriminator, and output a predicted probability that the image is real, together with some factors of one inputting into the cost function, and we use this loss to update the weight, the parameter of the generator. And for the discriminator, we will input noise to the generator so that we will create some fake images. And together with the real training sample, and the fake images generated by the generator, we will input it to the discriminator. And to get an predicted score that the images is real, we input this into the BCE loss function along with the ground truth, so that these inputs are real or not, are real or fake, into the BCE loss function, and then we will use it to update, backpropagate and update the parameters of the discriminator. Okay, generator with this counter. So in summary, GANs train in alternating fashion. The two networks are competing with each other. Generator is trying to fool the discriminator to produce realistic fake images, and the discriminator is trying to distinguish between the real and fake. To use the GAN, we need to save the trained generator for future sampling, or for it to generate more generative image, new images, normal images. So we can do some Q&A. How does the discriminator learn over time? Using feedback from the generator, receiving user input, comparing the images to the ones on the internet, or getting feedback on if its classification was correct.
Best answer.
Yes, getting feedback on this if the classification was correct. Yes. How does the generator learn over time? Using feedback from the discriminator. Yes. Well, perfect.
Can I ask a question?
Yes.
Let's go back to the diagram showing the flow of the training of the generator.
Yes.
What is the criterion here? The cost function of the generator?
It's BCE loss. This is part of the BCE loss.
But isn't the BCE loss the cost function of the discriminator?
Both both is using BCE loss. But then like it's different. You can think of there is two BCE loss function, and then the one for the generator is updating the weight of the generator, and the one for the discriminator is updating the weight of the discriminator. Yes. But what is so fascinating here is that and this is actually what Ian fellow thought of is like, why don't we use two neural networks to train each other? So that's why GANs is so breakthrough, is because of using two neural networks to train each other's parameters. And the key here is really like the factors of one being inputted. When we train the generator, we are inputting factors of one as the ground truth, when actually we know that everything is fake.
Yeah, because this is what we want to achieve. We want the discriminator to think that this is a real image.
Yes.
This is like the destination
Yes.
probability we're aspiring to achieve.
Yes, exactly. So we are actually cheating here at this point.
Yeah.
And that's why this is the key of GAN here. Okay, so let's move on to convolution. And after the convolution part, we can take a break. So just now we have seen the basic concept of GAN, And both the generator and the discriminator can take on different architecture. So in the code that you're going to, in the hands-on coding section that you'll be doing today, it will be a simple neural network. But both the generator and the discriminator can actually be convolutional neural network. And this is called DCGAN, deep convolutional GAN. Okay. So what is convolution? Convolution is an image processing technique where we apply filters into the images to identify features like eyes, nose, ears, etc. And let's go over the convolution operation. So we will need a grayscale image or a RGB image of like 3 layers. But then it will be just like the convolution is just similar fashion. So first we have a grayscale image here, and we have the convolution symbol. We have a filter. Okay, the grayscale image is 5.5 here. The filter is 3x3, and our output desired output here will be a 3x3 matrix as well. So we will move the filter to the top left corner of the image. We'll put it over, and then we will just do a product, a multiplication of each pixel of the image and the number in the filter. So we multiply it, and then we will just sum over, and then we put it in the result matrix. And so here we are doing stripe equal 1. So after we finish this process, we will move the filter 1 step to the right, and we will repeat the process. And then after we finish the second square in the result matrix, we will move again the filter to the right. And we will do the same process. And when the filter hits the most right column of the image, we will move the filter back to the left. But then this time we will move 1 step down if the stripe is equal to 1, which we will go over what the stripe is later on. And then we will do the same convolution process. We take the product of each pixels, and then we will sum it up until we finish filling in this resulting matrix. So in summary, convolutions are useful layers for processing image. They scan the image to detect useful features, and it's just element-wise product sum. And now let's go over stripe. So stripe is another image processing technique that determines how the filter scans the image. So here, stripe is equal to 1. So we will put in a similar fashion, we will put a filter in the top left corner of the image, and then we do the convolution process. And after we finish, we put the sum of products here, 150 in the resulting matrix. And then we will do it, repeat. The stripe is equal to 1. It's basically what we have just talked about when we talk about convolution. And we keep on doing it when the stripe is equal to 1 and we finish. When we have a resulting matrix. And when the stripe is equal to 2, we simply move the filter 2 pixels at a time to the right. And when it hits, so we do the same convolution process. And we'll move, after we finish the first step, we move 2 pixels to the right, and then we will do the same until it hit the most right column until the filter hit the most right column of the image. We will put the filter back to the left and move 2 pixels down. So, and then we will finish. So this is when stripe is equal to 2. So let's talk about padding. Padding is another image processing technique where we want to give importance to every pixels in the image. So you can see here, when we don't have any padding and when the strike is equal to 1, we have a 3 by 3 image here, and the filter is 2 by 2. So when we do convolution here using the filter over the image, the center's pixel gets visited 4 times, but the corner's pixel gets visited only once. And we want to give equal importance to every pixel of the image. So we add some paddings to it. So this is one padding equal to 1, where we add an extra rows or columns in both in the 4 sides of the image, left, right, top, and bottom. And in this way, when our 3 by 3 image become a 5 by 5 image, and we apply the same filter to it, and it will convolve, and every pixel within the image gets visited the same number of times. So in summary, stripe determines how the filter scans the image, and padding is like a frame on the image. Padding gives similar importance to the edge and the center, and every pixel in the edge and the center of. So this is pooling. Pooling is another image processing technique where we actually reduce the size of the image. And imagine we have a 2 by 2. We are talking about max pooling here. There are different kind of pooling. So imagine we have a 4 by 4 image in here, and we want to do a max pooling using a 2 by 2 filters with stripe equal to 2. So here we put the filters on the top left corner of the image, and we just take the maximum number of pixels, which in this case is 20 here, and then we put it in the resulting matrix. And since stripe is equal to 2, we move 2 pixels to the right, and then we take the max, so it's 45. We hit the right column, so we move the filter back to the left, but then move 2 pixels down, and then we get here this box, which is and we get the max, so it's 10. And then we get 42 here. So we are done with the max pooling. So in summary, pooling reduces the size of the image. There are different pooling techniques. So the max pooling, min pooling, and average pooling. So here is the code deep convolutional GAN called Snippers. So basically, everything, the architecture of the GAN stays the same, like what we talked in the previous section about the vanilla GAN. So everything is actually the same, the training, the loss function, etc. Except that the architecture of the generator and the discriminator is convolutional neural network. So here, this is the generator. So here is just giving some input and output dimension of the layers, of the input layer, the hidden layer, and the output layer. Here you can see that we are using convolutional transform 2D here, which is the convolution neural network.
I want to make sure you don't forget about the break.
Yes, I will forget. We are about to get into the break after this call. It's easy GAN call. And so here is the discriminator. And so again, here is just the code to give the input and output dimension of the input and output dimension of the input layer, the hidden layer, and the output layer of the discriminator. And here, like you can see that we are basically using conv 2D here for our network, which is the convolution neural network. And basically everything else is the same. And you will do a vanilla GAN in the coding section. So you will do your own GAN. So here we are, let's look into the fake images and the real images over time. So the one on the left is a step 500, means the 500th batch here. So you can see that in the beginning, the random factors that we are inputting into the generator is actually, when we visualize it, it just looks like gray here, gray squares. And at the bottom is actually the real training set of the endless digit. And then over time, when we train our GAN, when at step 13,000, we can see that the GAN starts to generate really like realistic images that looks like the endless digit.
So which epoch is 13,000 batch?
130, yes, is batch. It's not epoch here. So
Still not done, right?
and still not done. We can still continue. Like we can still see some artifacts here, and in the generated output, but we can see that it's pretty like much more closer to the endless digit than in the beginning.
Your network, do you remember how it looks good in your
I remember I used 200 yes. So make sure that you guys like have a culture daily limit in your Google Colab because you will need that. Now we're finished with the DC GAN, and so just now we looked at vanilla GAN and the DC GAN, but then you can not really control what you're going to generate when you input a random noise factor into your saved generator. Like you cannot tell the generator that I want to output a 1, give me a 1. You cannot do that. So now we want to give more control on what we want to output. So after the break, we will be talking about conditional generation and controllable generation. So let's take a 15-minute break, maybe. Okay.
no.
There's one of the issues was one of the power quality generates from your. Yeah.
Inside the nut.
Yeah. So there are tactics. And actually, my generator has an it's a time series sort of application. So I have.
Wait, what's the representation? ECG, no ECG.
Yes, I was doing the ECG.
Yes, exactly. So it's like, but there is how many channels people check?
Please.
It's already 12,
Yes.
and this 12. Okay, yes. So, and how we represent it as numbers? Image. You're not.
But you also have
Ah, 60 time. Good lines.
but like you really need to decide. Maybe just do you try to lose it? How many 5,000 volts? I think it is.
Well, is there?
Because you're not, what is your name? Just when you're inside. So we are not using images. No, just maybe you guys start with
I would think we should stay season. That's. You can
okay.
yes. You can do it. And in fact, it's speed. Okay, so you do.
Yeah.
Okay, it's still. Yes.
When I first started,
Right.
I appreciate it. So when everyone's working, it's just, and it's, okay, I can see it later.
Maybe some other day.
Or, yeah, we can, maybe we can have it. Oh, I appreciate it. Yeah, thank you very much.
Yes.
Yeah, I do have. Are you okay? This week a little bit. You wanna talk about now or later? When you
See you before the comparative.
sorry.
Tomorrow. I think things after you can go out between the thing in this.
So Thursday comes, Wednesday comes.
Wednesday.
Maybe my WhatsApp.
יצא, כן, לא נכנסתי לקרבה, לרזולוציה שכל ה... שזה לא נכנסים לזה, אבל זה גם יותר מדי כאילו חוזר על דברים שהם בייסיק, שתראו עליו. Videogram.
Yeah. And later, that's like more. I think it's like. Yeah, it's like. This really is like. And actually.
Yes.
Yeah, he said you can. I keep my word, I don't know, I never tried it. Do you have experience? Yes, I am. So that was like. So I have. Actually.
That's actually for you.
Oh, yes. I have colleagues that don't recognize me from my. But he's doing projection on. Oh, like everything. Different counterparts. Oh, okay, but this is like.
איך הכל גם זה פרקטיס זה כאילו תהליך disorders וגם הולך להיות שם היה משהו תמיד אצלם שאפשר לעשות זמן של מידע, מידע עצמה, לראות כל מיני יש עבודות על זה, אבל בכל מקרה זה גם לא מתאים. זה מה שאני כן.
אני חושב שלשתות זה דווקא it's not אתה ממש פותחים
כן, כן. עכשיו זה לא כמו שאני אגיד בשנה. כן, גם הטוב. כן. אם הייתי פזחתי. תהיה פרופסור. כן, הוא לא תופס לכל כך.
לא משחקים
השאלה אם הוא מודל שאנחנו כן, יש לי צ'אנלים, סבבה. תודה רבה.
Shall we start? Alright. So now we'll be talking about conditional generation and controllable generation. so that you can give a better control of your generator output. So with conditional generation, we are trying to get sample from a particular class. And with controllable generation, we're trying to control certain feature of a sample. So to make a better sense of what conditional versus conditional generation is, let's compare with unconditional generation, which we have seen earlier before the break. So in unconditional generation, we have examples on the distribution of images, NEDJ. And in conditional, so we are generating examples from the class that you want. And in a conditional generation, we are having a training data set that doesn't need to be labeled. Whereas in conditional generation, the training data set indicates the class for every instance. And we're going to use one-hot encoding to indicate the class for the training set. So here we see the generator's inputs. As before, the input is a noise factor. But then this time we need to label our data. So we will do we will achieve that by one-hot encoding. So for example, if we want to label the class 8. So if, for example, we are taking the Emily's data set as an example here. So we have 10 entries here in the one-hot encoding factor, and we put 1 at the entry that is representing class 8 here, and which is the second to the last entry of this in this one, and the rest of the entry we put 0. So, and then we concatenate the noise factor and the one-hot encoding factors together, and then we will input it into the generator. So, and the generator hopefully will output an image of class 8. So, essentially, the noise factor adds randomness in the generation so that you can produce a diverse set of samples. And now you are generating a diverse set conditioned on a certain class. And the one-hot factor is what lets you control both the class to generate. So let's talk about the discriminator input. So the discriminator's input will be and this image of in this case is class 6, and then we label it as class 8. We input this into the discriminator, and hopefully it will output a low real score here. So the discriminator takes the examples and paired with the class information as input to determine if the examples are either real or fake representation of that particular class. So in this case, we are inputting an image of class of 8 together with the class information, which is 8, into the discriminator. This time, the input images is a correct or real representation of class 8. So
for the discriminator, you only for the one-hot encoding, you only give this discriminator that specific class, right? So if you want 8, you only give the discriminator training sets of 8.
Yes.
Because you need the prediction for the 8 actually.
Yes, but then you will also have other Emily's data. Emily's teacher, you have 0, you have 1, and 2. So if you are doing inputting into the discriminator a 0, well, we are talking about the real training data set here, not the fake images. So we need to put a correct class for it to learn. Otherwise, it won't learn.
Yeah.
It learns to identify the matching. When
8 and
noise, between the 8 and the.
Yeah,
the
exactly.
class. Yeah, so, but it's not a separate, it's only one
I
discriminant.
don't know.
So, and it's really nice that you bring this up. So the training set, the real images that you are inputting into the discriminator, you need to put the right class. We will see how we put it later. We need to give the right label in order for the generator to get feedback from the discriminator to learn how to generate image of respective class. So here, since the class, the image is matching the class information, so the discriminator hopefully will output a predictive probability of high probability that is real. The discriminator will learn to predict that the image is movable only if the example looks like a cat. And the real images will have the correct class label. So the feedback of the discriminator encourages the generator to generate images to take on the right class as well. So let's look into how we are going to label our data set in for the discriminator input. So for example, we have an image of 8. So and MNIST data set. So here we have the MNIST data set is grayscale, so you only have one channel. But if it's an RGB image, you will have 3 channels here for the image. And then we do the we add like for this case, we are having an MNIST digit, so we have 10 class here. So we add 10 matrices, and the matrix that is represented class 8 is filtered with 1, and the rest of the matrices that is the 1 is the black one that you've seen here, so it's filtered with 1, and that matrix represents class 8. And the rest of the matrix is filtered with 0, which is doesn't represent class 8. And we concatenate these one-hot matrices together with the training image at 8 here. And so these are the input of the discriminator and the generator respectively. So let's look into how we train this discriminator. So first, we need some fake sample. So we need the generator to generate fake sample. So we input noise and the class C. We concatenate the noise in class C and input it into the generator. And then we will the generator will output a fake image. So, and later on we will talk about what this class C here is. But we will, so let's move on, talking about the fake image that the generator generates. And then we concatenate it with the one-hot encoded places. So also take notes that the input of the generator, the class C and the noise here is the class C is a factor, is a one-hot encoded factor, the C. And the input of X hat and C, the input of the discriminator, the fake images, together with the class C, when we need to label, we also need to label the fake data. So we need, here this C is the one-hot matrix. So also, when we input to the discriminator, we also need to input the real image, which is denoted as X here, together with concatenated with one hot encoded matrix of class C. So we input the real image and a fake image into the discriminator, and then we output a predicted probability y hat z, whether this real this input is a real representation of the class. With this y hat z, we input into the loss function. In this case, it's the BC loss. And then we need to give a label y, which is a ground truth where these images are real or fake, or is a real representation of the class C respectively. And then with this loss, we are going to backpropagate the parameters and update the weight of the discriminator. And here, we are looking at how we train the GAN to train the generator. So to train the generator, first we input some, we have the noise factor, and we also have the one-hot encoder factor, class C here. It's a factor here. So we concatenate the noise on the class C and input it into a generator. And you will output an image. In this case, is a 28 by 28 pixels of big images. And then we need to attach the one-hot encoder matrix here, and then concatenate with the big image, and then we input it into the discriminator. The discriminator will output y hat d, the predicted probability that the input is a correct representation of class C. And then we have this y hat d input into the cost function together with the factors of 1. In a similar fashion that we have talked about before. With the cost, we use it to backpropagate the parameters and update the weight of the generator. So I want to talk a little bit about the class C here. So since we are training both the discriminator and the generator iteratively, so first with a batch of data, we will use it to train the discriminator, and then with the same batch, we will train the generator. So every batch is labeled from their training data set, right? So this the class C is actually taken from the label of that particular batch for both discriminator and the generator.
Every batch will have X C's.
Yes, yes.
I have a question about it, because you have a lot of images between 0 to 9 in that training set.
Yes.
And then you have unbalanced data, because when you're training about 8, you have 1/10 8s in your data. Or
1/10.
Oh, but we don't only train 8s. We don't only train
no,
we train.
Using 1/0, so you have 90% of the training set.
No, when your training image is a 0, you one-hot encode it in class 0. So the 0,
your real is X and C, so that X represents C. That's the real. So you see, it's both. That it's a bit confusing, right? Your instances, maybe you should say this again.
You mean this part? So for example, if you have a image that represents a 0 digit, so you won't it should be the first layer here, the first filter to be 1. So this one will be filtered with 1, and the rest is 0. If we have digit 0 here, if we have digit 1 here, so it will be this one to be filtered with 1, and the rest is 0. So this one-hot encoding matrix should be representing this digit. In this case, it's 8, so it should be this digits because it's 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah.
Why do we use one-hot encoding matrices and not one-hot encoding vector that we concatenate to the flattened matrix?
Here we are using the factors because the noise factor we need to match the dimension. So here is the noise factor. So we are having, only one column, but for the input of the generator. So, but here for the discriminator input is an image. So we need a matrix to actually encode to label this data, this image here. There are other ways to do it, like to save space, and we can talk about it later after the class. But like there are other ways to do it to save space.
Yeah,
This is just like one example.
Okay, so when we concatenate the vector or the matrix, doesn't matter to my noise, and when I get the output is not the same size as the input, so it's already concatenated. Why should I concatenate another C?
So here, let me go. So here, is a factor. If your batch size is 5, is a 5 times 1 factor, and this one is a factor. So these together, after concatenation, imagine you are doing the analysis data set. So you have 10 class. So this should be a what? 15 by 1 factor, right? Your batch size is 5. So we input this, and this X hat, what is the dimension of this one? It should be outputting 28 by 28 image, right? So this X hat is an image here. So when this C should be a matrix, because this is how we do the one-hot encoding and concatenation, right?
So
So this C is a matrix.
So the noise input and so the generator input and the output are not in the same size.
Right, exactly. This is a factor, and this becomes an image. So it's a matrix.
If this is technical, why do you need this matrix? I'm not clear, but it's probably
Because it's an image.
you have a shape of a tensor or a number.
Yeah, we want to also encode. We need to label also the fake images for the discriminator to learn. Because the discriminator
is find the filter between this and the next uniform way, and you don't want to leave it. That's why you make it into a matrix, right? Otherwise.
Yes, we need to make it a matrix. Basically, we need to match the dimension of the image. But then in the code, when we see the code, it will be more clear because we are making it dynamic. So you don't really need to specify like the dimension. What if you are encoding a factor or encoding a matrix? You just they will get the dimension automatically.
Will match. Will match.
Yes, you will.
That's because it's technically easier to define the filter of that. There's no more information in the one-hot matrix than in the one-hot vector. But
yeah, exactly.
in terms of programming, it's probably easier. That's my
Yes. Yes, I agree that it doesn't save problems. Like it's quite space consuming in the one-hot encoding of the matrix, and there are other ways to do it. So here is we talked about here, and this is also we talk about how we train the generator. So when we train the generator, we input also noise factor. We label the noise factor. We input it into the generator, and it will output a fake image. And the fake image we need to encode it to label it too. And then we input it into the discriminator, and the discriminator later will output a predictor probability if the input match the class. And then we input this y hat v into the cost function together with factors of 1. And then the cost will help to backpropagate and update the parameters of the generator. So again, the key here is the factors of 1 because we are the generator wants the discriminator to think that its fake images are real. And in this case, the fake images are matching the class. So here is just a repetition and reminder of how the loss function looks like and what other inputs. So in summary, the conditional generation requires labeled data set. Examples can be generated for the selected class. The class is passed to the generator as one-hot vectors, and the class is passed to the discriminator as one-hot matrices. The size of the vector and the number of matrices represent the number of classes. So here is the code snippet. I don't know if you guys can see it, but you guys have the presentation, right? Okay, you cannot see it, but I will explain. So here, what you see is the code for the generator. It's nothing like new. It's actually the same architecture of the district that we've seen earlier. And this is the discriminator. But what is so special about the conditional GAN is here. First, we have the get one-hot labels. We simply do one-hot encoding of given the labels and the number of classes. And here, with this function, we are using it for combining the factors. So it's just combine. So if X and Y are factors, they will concatenate, and if they are matrices, they will also in a similar fashion concatenate together. And here is just to get the input dimensions. We want to know what is the dimension of the generator input and the discriminator input. Oops. Okay. And remember the number of class that we have in the training data set affects the dimension of the generator input and the discriminator input. I don't know if you guys can see. Try this. Okay. So here is basically the code that codes out the whole training of the discriminator. So first, line 1 here, we are actually getting the noise. And then 2, the second line here, we are trying to combine the noise and the one-hot vector. In line 3, we are putting this labeled noise into the generator to generate fake images. In line 4, we are combining the fake image together with the one-hot matrices. And then we also have the real image from the training data set, which is labeled. And then we input both real and fake images into the discriminator for it to output a predicted probability. And then we put this predicted probability of the real and the fake input into the PCE loss function. And then also we put the ground truth. You can see in line 7 here, we have torch.0 and torch.1 respectively, depending on if the input is fake or real. So after we calculate the loss, we backpropagate and update the parameter of the discriminator. So this is how we train this discriminator. So, and this is how we train the generator. And you can see it better here because the image is larger. So in the first line, we have we're trying to concatenate the fake image and the one-hot matrices as what you see in 1 here. So here we already put noise and the labeled noise into the generator in order to generate the fake images. Okay, so line 1 is we already get the image, and then we input it into the discriminator, and we get it. And in line 2, we get the prediction from the discriminator, and then we input this y hat d into the cost function, which is in line 3, together with the vectors of 1. We can see we are using torch.1's as the label, as the target in the second parameter of criterion in line 3. And then we just use the loss to backpropagate and update the parameters of the generator. So here we can see that is the fake images versus the real images over time in this conditional GAN. So in the 500 step is the random noise looks gray color. It doesn't look like anything. And at the bottom is the endless data set. And we can see in the plot that the beginning the generator is lousy, so the loss is pretty high. And in the 93,000 steps, we can see that the fake images is more endless digit-like. So, and we can see that at some point, the generator loss and discriminator converges as well in around step 1 plus. So what we see just now is the conditional generation. So now we will be talking about controllable generation. So we've seen just now with conditional generation, it leverages labels during training in order to generate output of the class you want. But with controllable generation, we can control the desired features, such as the pose, the smile, the age, the perceived gender, and with or without sunglasses, and the generator output, even after training the generator. So with control, this is what we are doing with controllable generation. So we already have a trained generation. Now, a trained generator. Now we want to tweak the features of the generated image. For example, here we can see that we input a random noise factor to the trained generator, and it gives an image of this boy with red hair. But then we want to tweak the noise factor so that the trained generation will give an image of a boy with blue hair. So and just for example, maybe is the first element of that the first entry of the noise factor is what is representing the hair color. So we just want to tweak that one for the trainer generator to output the blue hair pictures. So we are going to see how we're going to tweak the noise factor. So to give a better sense of what is controllable generation, we are going to make a small comparison between a controllable generation and conditional generation. And a lot of times in the GAN literature, conditional generation is also referred as a controllable generation, because in conditional generation, you are really controlling what you're generating. But like there are like still differences. So we'll see. In controllable generation, the examples with the features that we are generating examples with the features that you want. And in conditional generation, we are generating examples from the classes that you want. For example, the empty digit where class 1, class 0, class 8. And in controllable generation, we are controlling on we can control on how much or how little a feature that you want, such as a continuous values like hair length and age. With a conditional generation, we are like controlling the class, not the features itself. And in controllable generation, the training data set doesn't need to be labeled. In contrast to conditional generation, the training data set needs to be labeled. And in controllable generation, we are manipulating the noise factor input into the generator, into the trainer generator. Whereas in conditional generation, we are appending a class factor or matrices into the input. And in controllable generation, it happens during and after the training the model, whereas in conditional, it actually happens during the training. So
is it fair to say that
the main difference is in conditional, you have to decide what your classes are. You can't decide now I want the hair color. And in controllable, you can decide on.
After you train.
Yeah, you don't have to decide. You don't need to decide anything in advance.
Yeah, right.
What is it that you will want to change or especially?
Yes.
Conditional. I think conditional is more. If you know what you want ahead of time, conditional works better. But in controllable, you don't need to decide. You decide now I want to move the height, the hair color, or whatever. If I want either I don't know, tall people, short people, I know that ahead of time. I think I want to do condition, then I train. But I'm not sure. I think that's the.
Yes, I agree with you. And the main difference is also in conditional generation. You are trying to control the class of what you are generating. So let's take the MD-Stager for example. So you want to generate a 0, you can control that. You can tell the trainer generator that I want to get a class 0. Please generate me a image of class 0. But with controllable, we are trying to change the features of the image. For example, we will tell the trainer generator to give me a folder 8 or an 8 that is initialized or like string. We are trying to modify the features, the pixel of the image, not the class. So with controllable generation, it's done by manipulating the noise factor Z that is fed into the generator. So there are 2 ways to do it. The first way is by interpolating between 2 GAN output, and the second method is by manipulating noise factors in order to control the desired features. So let's go over the first method, which is interpolating between 2 GAN outputs. So here we at the left-hand side we see a plot of the seed space with noise factor. The seed space is basically the space of the noise, which is filled with noise factor. And Z1 is the first dimension, and the Z2 is the second dimension. And in this space, we have like a lot of noise factor. And here we see the noise factor V1, and also noise factor V2, which is like V1 is 510 here, and V2 is 45. So when you give this V1 into the trigger generator G, you output an image of the Indian girl. And when you give the factor noise factor V2 into the generator, you will give an output of the girl on the right-hand side, the Caucasian girl. And we can, so now we want to get an intermediate images using the seed space by choking the noise factor. So we can achieve that by using linear interpolation, which is, you can find a t, define a t in 0, between 0 and 1. And you can use t times v1 plus 1 minus t times v2 to generate different factors. Generate intermediate factors between v1 and v2. So with this intermediate factor, we can generate an intermediate images between v1 and v2.
Yeah.
So yes.
Just so I make sure I understand properly. So V1 and V2 are representations of generated samples.
No, V1 is a noise factor. It's a
The noise factor corresponding to the first image.
yes, exactly. It's like here. So
Alright, so
just to make it simple, we use 2 dimensions.
Right, okay, and then you took some convex combination of those two vectors and you managed to get a new noise factor, and you used this noise factor with the same sample.
Trained generator.
Pardon?
With the same trained generator.
Right, and so like the only difference is that we took two different noise vectors. We generated some linear combination, some convex combination of them, and we used the new noise vector to generate a new sample, which has to be some combination of the images corresponding to those two original noise vectors.
Yeah.
I'm not following. Like, why would what ensures that the resulting combination of the noise vectors, the new vector would have a behavior that elicits a result that resembles some combination of the original images, each of which corresponds to one of the noise vectors.
Okay, so first, like we have this B1,
Right.
and we give to this trainer
Yeah,
generator, we have this image. And we also have defined B2
Right.
that is inputting into here, this B2 into the trainer generator, and we will give it these images. Now, we want to just have an intermediate linear transformation from this image into this image. So, we will use this formula, meaning that the T can be this, which is called linear interpolation. So this T can be arranged from 0 to 1. So first, imagine, let's make T 0. So T is 0, that means we are canceling here and we only look at here. So you will be V2, which is this image.
Yeah, I can see that.
But then if we take a little, we make this T as 0.1, meaning that we are taking a little bit of V1 and 0.9 of V2, and then we are trying to generate these images here.
I guess.
In this way, we have this like intermediate factors,
Yeah.
which will give us an intermediate.
I understand that the resulting noise vector is a convex combination of the two original ones. That I understand that. My concern is about how the fact that the resulting noise vector is a convex combination of the two original vectors will result in an image that resembles some combination of the images that correspond to the original noise vectors. That's what I'm asking.
I think what's bothering it, it's clear that we're gonna be in a point in Z space.
Yeah.
The question is, you take this point in Z space, you pass it to a generator.
Exactly.
Why would you even get an image, but why would you even get a face?
Thank you
Let
for
alone-
exactly that.
Well, because
exactly.
What
Thank you for
happens-
clarifying.
And that's true, it doesn't always, it's true, the linear interpolation does not always, if the noise space is very dense and you really manage to generate a space from each point in the noise space, then it works. But otherwise it doesn't. You can show that sometimes you need to interpolate a certain manifold. And
Yeah.
the linear interpolation is the simplest one, but it doesn't necessarily.
I see.
So here we can see the another technique is the controllable generation, where we can see that it's actually similar to the technique of interpolation, where we are also manipulating the noise factors in the Z space. Here we still have like two noise factor, V1 and V2. And then when we input V1 into the trainer generator, it will give us a volume of red hair number. And when we input V2 to the generator, it will output an image with a blue hair. So the difference between V1 and V2 is the direction denoted in D here to modify the hair color. So and later on we will try to find this, and we will learn on how to find this D. So the goal here is to actually really find this direction D for different features you care about, such as hair color, so that you can control the features on the open of your GAN. So after you find this D, and you can do the same trick to any of the image, to any noise factor. So imagine we have another noise factor here, V1, which given inputting to the trainer generator, you will generate this image, a girl with red hair. And we can simply add D to this V1 to get V2. And then we will get, inputting to the same generator, we will get a girl with blue hair. So now we will learn on how to find this D. So in order to do this, first of course, we need the noise factor. And then we will have a trainer generator. And then this time we will be having a pre-trained classifier. And in this case, let's try to look at how to add beers to this lady to generate image with beer. So this pre-trained classifier is trained to identify if the image has beer or not. So and as always, we have a noise factor, we put it in the trained generator, and we output an image. Then with this image, fake image, we input it to the pre-trained classifier. And the classifier will tell me the probability that this image has a beer or not. And with this probability, it helps to modify the noise factor by moving in the direction of the gradient verticals that penalize the models for every image classified as not having beer. So in this way, iteratively, the noise factor will be triggered to generate it so that you will get to the noise factor that when you input to the trained generator, you will output an image of the lady with the beer. So we can see the code in action here, the code here. So first, we input some noise factor to generate the fake image. The next line, fake image history, is like really just for visualization of the fake images. And then we put the fake image into the classifier in order to generate a fake class score, like a probability that if the image has a beer in this case. And then we backpropagate this fake class score for it so that it will look for the direction of the gradient. And then you will do the trimming of the noise factor by using carefully updated noise. So here is the function of carefully updated noise. Sorry. So basically, we are doing a gradient ascent here, where we are trying to move up the noise factor towards the noise factors that is able to generate a high probability of images with beer. So that's why we are here, noise plus noise dot grad, the gradient, times some weights. We are using a plus here. In contrast with gradientism, what we're doing in propagation in gradientism on the cost function.
So one more. I think it may be correct. So the point here is we're doing gradient ascent on the Z space. So we're moving in the direction of the gradient in the Z space so as to increase the probability of appear. Our function is the probability of appear. I take the gradient of this function with respect to Z and I move in that direction. Now again, this does not work if there's no beard in my entire universe of the generation. If there's no, I can move on the direction of the gradient as much as I like, but the probability will never get to 1. It will go up maybe something, but it will never get to 1. If something like that is in my generation originally, it will make it. Even if it's only with men, which is with women, I can put the beard on.
Right.
Okay, but I had to have seen beards, otherwise, no.
Yeah, the model have to see samples with
With the feature that I want to push towards.
right.
And then it should work. It doesn't.
So in summary, controllable generation lets you control the features of the generated outputs. And it does not need to be labeled. So that the input factor is triggered to get different features of the output. When you control the output features, you need to find the directions of the gradient in the C space. So to modify your output, you move around in the C space, and the classifier helps you to find that direction. And this direction are the gradient of the classifier probability with respect to the noise factor C. And the updates are done just to the noise factors iteratively until you're able to generate an image with that beard. So in conclusion, GAN is made up of the generator and discriminator. The generator tries to produce realistic images that fool the discriminator, and variants of GAN can be used to emphasize features in the generated object, like conditional versus controllable generation. And let's enjoy the GANs and do some coding. I've sent out the Jupyter notebook where you can like code the GAN. So I think everyone has a Google account here, right? So
Yeah.
let's do it on Google Colab and connect it to the GPU. So that it will be much faster. So, and if you have any
Thank
questions.
you, Abigail.
Thank you. And if you have any question about the coding, like please let me know, and then like we can look into it together.
So we now
You can
open
start the coding section.
break.
Maybe a couple.
Yeah, you guys can. We have time until 9, so enjoy. But then I believe you can finish. You can also take a break. I think the coding you can finish it in 1 hour, but like we can finish it till 9. We have time until 9.
Parallel, we do it like in the same, like all together, or everyone does it by itself?
Everyone does it by itself. You will receive the Jupyter notebook
Yeah.
in the email. So you can upload it to your cloud, Google Cloud, and then open it with collaboration. Let me know if which
Che adesso mi
Like this one, yeah. Because now the generator. Now the generator is running something generator. Zeros and products. Trying to optimize.
Distinguish if it's a real representation, the image is a real representation of the class. Eight. So at the end of the day, we are so here we are entering assumptions because we are trying to tell the generator what you are outputting, and this here, remember, is actually matches the big image is matches with this thing. It's not because this C here is actually the same C as the image. So this we are trying to have this same image and telling with this. So yeah. So the only difference is this is a real. This is a real from the real training side. So in a way, we are still having an output of real and fake here, but this time.
Yeah, it's kind of like
yes, like
instead it puts a real
we are not no longer a real image but a real if the image is a real representation of the class.
Yeah, so why the generator is not the same loss function? Like this image is a real representation of the class. That's why I'm asking because that one is no longer answering this image forms in class.
Because we are trying to tell the generator what you are generating is actually a real weapon is representing.
Yeah, but it's optimized enough. Screen. Like so different loss pages. Like it's no longer the same goal. This is what control before the conditionality is right. The generator is doing something else different. So it's going to do next.
So yeah,
It's interesting.
it's like if you can
Yeah. This one instead of all at once.
so you're meaning that here
Instead of all ones here, just one in the right class. Zeros and the rest. Because I want this number to go high. And then one all of them to go high. I no longer want all of them to
you
go
know
high.
this one is 4.5 can be so for example we have this can be represent the noise factor that helps to generate digit 0, this can generate digit 1
Yeah.
or digit 2.
And
We
then I
don't
still want
care
them to
about
be
the
high
class.
as much as possible, closer to one.
Yes. We don't care about what us. The goal here is that we are telling the generator is generating big images that actually matches the class. That's why we're telling here like the factor of 1 instead of 1 or 0.
I think that even
The one should
Even if we do only one, the automated one, kind of achieve the same result. Or this specific task, but not sure. Attention. Okay.
What's this?